Well, hello everyone. Welcome to 3D Native's latest webinar, How to Optimize Your Designs for SLS 3D Printing. My name is Madeline Pryor, and I will be the moderator of this discussion today. I am here with Alban, the CEO of Prodways Printers and Solidscape, and Dave Hockemeyer, the owner and co-founder of PERIDOT Incorporated. Good afternoon, or rather, good morning, gentlemen.
Good morning, Lauren.
Great. So, just so everyone knows, I will introduce myself and the panelists in a little bit. But before we get started, and while people are still trickling in, I just want to take the opportunity to send a survey to you all. It will be, so you should all be seeing it on your screen right now. This is just to get a little bit more information about you and about your expectations so we can help tailor the webinar for your needs. If you could just take some time to answer this, we can, this is also just useful to do while people are still coming in. It always takes a little bit of time. So if you could just answer, that would be great. And at the end, I will also show you the results. While people are answering those questions, I would just like the opportunity to tell you all that this webinar will be recorded. You will be able to find it afterwards on 3D Native's YouTube channel if you would like to rewatch it. And if you would like to be notified when it's put up, feel free to subscribe to our YouTube channel. We have a lot of other content as well, all regarding 3D natives, not 3D natives, sorry, 3D printing. So I'll just give you all a few more minutes because we just have some more people coming in to answer all these questions, and then I will broadcast the results. Let's just take a moment. Thank you so much for responding. It's helpful for us as the moderator and the panelists, and also for you guys just to get a better view of who is attending this webinar today. And we have people still responding. Just a few more seconds. If you haven't responded, please, we really do appreciate it. And it's really just for our information. Okay. Okay, so I see that the majority of you have responded already, so I will end the poll. And I will now share the results with you all. So the first one, so I see that most of you do have a 3D printer with using either other or FDM printer, and you're mostly doing it for production and functional parts. That's very good to know. You're very much in the right place. So just so we can move along to the introduction then, if we could just move to the next slide. Great, so as you can see here, we have the agenda for the next hour or so, which is up. So as you can see, this first 10 minutes will be the introduction and a brief overview of the AM market, especially the polymer market for any of you who do not know it. We will then move to the presentation, which will go into a little bit more, which has been broken into 3D parts, and which will start with if you should be using SLS for 3D printing, before going more in depth on tips and tricks for optimizing SLS, especially in the design process, and giving you some examples of specific user cases. As you can also see, the final 15 minutes of the webinar will be a Q&A session where you can ask questions directly to our panelists. Throughout the webinar, do feel free to ask these questions. It doesn't just have to be at the end. If you look at the bottom of your screen, there's a Q&A box. I ask that you ask your questions in that section. It means they will all be kept in the same place, and also that it won't get lost in messages. And at that point, you can ask at any time, and then I will moderate as well at the end to get as many of your questions answered as possible by our expert panelists. So moving on to the next slide, we can start the presentation. So as you may or may not know, in additive manufacturing, polymers are by far the biggest part of the industry, though you can of course use a variety of materials such as metals and ceramics. Polymers really could be said to be the base of AM, and that has been confirmed even in most recent years. A recent survey showed that in 2020, 85% of respondents were using plastics and polymers compared to only 23% who used composites and 21% using carbon fibers. So even though we have, of course, there is some large numbers because there are people who use both, but you can see that AM is still very much dominated by polymers and plastics. It also is showing no sign of stopping, with immense growth expected with high performance polymers like PA, PEEK, and PEC, and it's expected to grow 22.9% between 2020 and 2025, expected to be worth 202 million in only 4 years. Out of all of the AM techniques that are available, many of them are used as well with polymers, including what we will be talking about today, which is SLS. If we can move to the next slide, please. Great. So in case you don't know, selective laser sintering, or SLS as more commonly known, is one of the most popular of the AM processes. It's also been gaining in popularity in recent years. Unlike many of the other methods, it's part of the powder bed fusion process, which is often actually associated with metals. In this case, a polymer powder is dispersed and a laser is then used to create parts layer by layer. As you can imagine, or maybe already know, this allows for geometries and precision that is just not possible in other processes and certainly not in traditional manufacturing. The method is especially known for its speed and precision and is used in many industries, including design, automotive, aerospace, engineering, medical, and many, many more. It is especially interesting for manufacturers as well because due to its nature, it does not require printing supports, unlike many other processes like FDM, which saves people both costs on materials and time. However, it can be difficult to ensure that you are optimizing your design to make the most out of the SLS processes, hence the webinar today. Now, I would just like to introduce you to myself and the panelists. As I previously stated, my name is Madeline Pryor. I am the English content specialist for 3D Natives, the largest online media platform for 3D printing, available in 4 languages, English, of course, but also French, German, and Spanish. I will be the moderator of the panel and the Q&A. And then again, a reminder to all of you that during the event, you can ask any questions you may have in the dedicated Q&A section. These questions will then be answered at the end. Now to introduce you to our panelists. Alban is the CEO of Prodways Printers and Solidscape, which delivers enhanced products for the benefit of all its customers as it expands its 3D printing technologies for the dental, industrial, and jewelry industries. Alban has 15+ years of experience in strategic business development in the high-tech industry and his engineer background to cultivate synergies between Prodways Printers and Solidscape, where he also serves as CEO, as previously mentioned. Alban has been overseeing the development and launch of Prodways' key products for additive manufacturing since he joined the group in 2015. He also holds an MS degree in engineering sciences from Harvard University in Massachusetts, with studies in applied mathematics, and an engineering degree from the École Polytechnique in France. Just a little bit more for anyone who for some reason doesn't know it, the Prodways group is based in France and in the US and is one of the leading 3D printing manufacturers in the world, known especially for their moving light DLP and of course plastic laser sintering. They work in a number of industries, as previously mentioned, and with their selective laser sintering range, it's pretty unique because it includes not just entry-level printers like the P1000 series, but also high temperature models, which go up to 280 degrees Celsius, and industrial productivity models like the 4500X. So our next panelist is Dave Hockemeyer, who has a mechanical engineering degree from Purdue University in the United States, with prior experience in the automotive, aerospace, and polymer industries. Dave is the owner and co-founder of PERIDOT Incorporated, an advanced manufacturing company that utilizes additive and subtractive manufacturing to serve a variety of industries. With over 20 years of experience operating and applying various types of 3D printing technologies to an array of applications, he has an understanding of both its effectiveness and its limitation. PERIDOT Incorporated is one of the longest running additive manufacturing service bureaus, over 20 years in the United States. Out of its many available processes in its manufacturing arsenal, it also includes selective laser sintering. Welcome, gentlemen. Let's begin.
Thank you.
Thank you, Madeleine.
Just move to...
That's good. Well, thank you. I'll go quickly on this one because you already gave quite a few numbers, Madeleine, on the market. But indeed, we've all seen last year that additive manufacturing has continued to grow, especially the polymer part. It's represents a significant portion of the market, and it's actually it's been used widely in the previous years, and it continued to grow. And that's why we continue to focus on developing industrial application for the polymer. If we do a focus on the polymer, I'd like to share with you on the next slide one of the graphs that was shown by Sculpteo. Sculpteo publish every year what they call the state of 3D printing, and the report for 2021 was just recently published. And that shows what kind of technology are being used, either in-house or externalized. We have a slightly different flavor from what we got from the survey, so I'm happy to welcome all those that already own a printer. But you can see that SLS is the #2 technology to being used, and it's also massively outsourced and not necessarily insourced. And so it will be good to discuss today what are the barriers and what we can do to better use SLS as a 3D printing technology. Again, we showed the principle, and I'm sure that most of the people in the audience are familiar with SLS. Just 4 key points that will help us understand what needs to be optimized and what is really particular about the SLS process. The first point, obviously, is that we're working with thermoplastic in a powder form, and that's an important part in the process. It gives you the ability to not have support, but it also gives you the need to process powders that are volatile, that you need to store, you need to mix, and all these are part of the process overall, and are taking actually an important part of the task that you need to perform around SLS. So we'll discuss this also later on. We're working with a laser to sinter. The result of the laser is that the laser size, the position of the laser will directly drive the accuracy of the part you can build to the limit, of course, of the grain size that you can find in your powder. You can have coarse powders or finer powders, but that will be the limits. And conversely, the speed of your process, how fast you can finish your job, directly depends on the laser power and on the number of parts, on the heights of the build. But even at the same build height, it depends on the number of parts. So this gives you some of the knobs that you have available to optimize the use of SLS with this technology. So let's start to address the first part, which is to discuss when is it suitable to use SLS, and then we'll discuss once you're using SLS, what can you do better. So this is the biggest question. So I have a design, I have a project, I have a part, and we're asking the question, should I use SLS? Well, there is an answer to this question, and the answer is maybe. And that's what we're going to discuss now. So the real point is that if you are looking at a functional part, a part that has an end use, that you're going to manipulate, that you're going to place somewhere, then you must explore whether SLS is a viable option. It's definitely a competitive solution. It definitely brings functional material that have that can match your application. And so you should explore, make your ROI, and define whether SLS can be used, because it can definitely, in many situations, be a good pick for your application. And so in particular, what are the key benefits that we see from SLS? So the first thing is that it's a low cost per part and a high productivity with no support structure technology. Now, talking to cost, of course, we need to compare with 3D printing and with other manufacturing technique. Depending on the complexity of your part, it can be a much lower cost per part. If you have a very simple part, of course, there are some other manufacturing techniques that can do a better job. But compared to other 3D printing technology, the powder is one of the cheapest source of material. And even in the recent years, we've seen even more powder coming to the market with attractive prices, volume prices, and so it's really allowing you to get a really good cost per part. It's also a technology that gives you access to large building blocks, so you can manufacture a lot of small parts in a single job. You can manufacture larger parts. So it gives you quite some flexibility in terms of manufacture build profile. And we hear more and more story of small series production using SLS, and that's thanks also to this large building block. And of course, the last point with SLS, it's one of the 3D printing technology that give you the most design freedom. We'll go again around the design constraint, but honestly, beyond the enclosed volumes, you can design pretty much what you want. There is no support to be removed, not many constraints. So it's a very flexible approach to design functional parts. So some of the use cases that we see emerging on the use of the SLS technology: functional prototyping and use production. So, and it's not new. It's been around. We see more and more production parts growing, but functional prototyping remains a key usage of SLS. It's becoming a more and more popular alternative to injection molding, and last year has demonstrated fully the stress we can see on supply chain, and the ability to have a local manufacturing that you can control, that you can scale up, accelerate, decelerate at any time, is really a very interesting asset to get with SLS 3D printing. And so any low to mid volume production can now be a good case for the SLS technology. So that's really some of the key area where we see the use of SLS. In terms of vertical markets, you can find SLS pretty everywhere where you would have some polymers, automotive, aerospace, but even consumer products. So there is really no specific vertical market for this technology. So the last point about SLS is, well, if it's that great, why are we not producing everything in SLS? And it's true that, as you see, a lot of people are externalizing it or not yet using it by themselves. And that's because we've seen a few common objections to the technology. So the first thing we usually hear is that, well, SLS, still it's expensive. And that goes with 3D printing in general. Also, well, double check. I mean, it has been growing a lot recently in the recent years. More material, more players. We've seen many large chemical companies join the SLS industry, and the example of the polypropylene from BASF that's coming from the injection molding, that is a known material that's coming with a competitive price, is a good example of a material that really gives you access to lower cost per part. The second objection that we hear is the surface finish of the SLS. Because you're working with a powder, as you sinter the powder, you get a grainy surface. First, there are some very good powder that are finer, that have a narrow grain distribution that give you a smoother surface finish. But also we've seen emerging in the industry in the recent years, again, more and more players offering great post-processing solutions and that are fairly easy to use now. Whether it's polishing, coating, plating, there is many ways to also transform the printed part into a final product that you cannot guess it was 3D printed. Third one is the material offer. Originally, SLS is linked to PA12. So we had years and years of doing PA12 and actually doing probably only PA12 white only. And this has changed a lot. So check again. You can find now some great flexible elastomeric material, TPU, for example, medical grade, food grade material, tough material, glass field. The living hinge effect that you can get from the polypropylene also is something new. Abrasion resistant material, conductive, resistant, glow in the dark. So there is really a very wide range of material. The interaction between the machine manufacturer and the material provider has really accelerated in recent years. And so there must be a material that should be close enough to your application. Finally, powder is dirty. That's something we hear a lot. And well, it's not totally wrong. You know, managing powder is more complex than managing FDM, where you just have a roll of filament. But with the proper setup, if you organize yourself around the powder management, that's fairly under control. And yes, it's an industrial product, but it's something you can totally put under control. You just need to plan ahead and be able to address the powder in your system.
Okay, thank you, Alban. Hello, everyone. All right, so to expand on that a bit on some of the objections that Alban just mentioned, parts are too expensive, surface finish, etc. It's very important to put those types of commentaries or those types of aspects in perspective with what are you comparing to. It's really important if you're comparing to other 3D printing technologies, SLA, FDM, etc. Yes, some of the commentary you just heard can apply, but if this is really additive manufacturing, those different aspects need to be compared to other manufacturing processes. For instance, too expensive. Compared to FDM, many of the filaments, yes, FDM filaments can be less per kilogram, but they also can be much more expensive than, say, the polypropylene developed by BASF. Compared to SLA resins, the powders are significantly lower cost. Smooth enough. We'll touch on the materials specifically, but the particle size does vary, and there are many surface treatments being developed. The number of materials are evolving quickly every year, so there is a diverse type of material available on this SLS technology, so that just needs some homework done. And then the last one that Alban mentioned, powder is dirty. We'll touch on that a bit further, but yes, compared to an office 3D printer, yes, that could be argued. Compared to an injection molding machine with lots of ancillary equipment, it's not as dirty as that. So it's important to look at these different aspects with respect to what? With respect to whatever it is you're comparing to, which can vary in every case. So as we move on to design considerations and limitations, here's some hard numbers, not to bore you, but things such as in this SLS technology, and most of this information is coming from the polypropylene material. Wall thickness. Yes, all of these are part dependent, but about 0.5 millimeter is what we recommend as a service provider that's been in this industry for over 2 decades. 0.4 millimeter, 0.5 millimeter. Hole size. When you start getting down to 2 millimeter diameter and under, it starts to get challenging. There'll likely be some secondary ops to qualify your hole. Escape holes. Those need to be considered. That's hollow areas that have excess powder in them. How do you remove the powder? It's just part of the technology. If you have a single escape hole, we recommend about a 5 millimeter diameter. If you have multiple escape holes to get the powder out, you can make it smaller, about 3 millimeters in diameter. A common question is minimum feature size. Well, again, that can vary a bit, but 0.5 millimeter to 1 millimeter is about as small as we recommend for polypropylene. And even that, a consideration or something to keep in mind is this is a heat-based technology. Heat is being introduced to the powder bed. So let's say you have a very thick section, a heavy wall, and your next part in the build or a feature on that is a very small feature. There is some experience factor and some consideration, and in this case, Prodways is very supportive to provide assistance in that. But when you have a heavy section, i.e. a lot of heat and mass, and that's followed up with a small feature, that can be challenging. So considerations have to be made for that. Moving connected parts. What that means is, can we start building assemblies? And the exciting answer is yes. Again, SLS has been able to do this for some time, but as these powders and materials become more applicable to production, we can build multiple parts in the same assembly, which, what does that do? It reduces downstream assembly, which is a big labor savings. Another common consideration we get asked is text. We recommend roughly 0.2 millimeters high by about 0.4 millimeters wide. We have lots of parts that we build that has lettering. Tolerances, again, about 0.25 millimeter plus or minus, and then we add a 0.1% scale factor, depending on a very small part or a very large part. Part quality, Alban touched on that a bit. It does vary a bit by, surface finish varies a bit by powder, but we are finding that part quality, or I like to say consistency, is very good. We run multiple technologies in our company so we can compare them head to head, but part quality is nicely consistent. Orientation is always a factor in additive manufacturing. The XY strength is consistent, the Z strength is similar, but orientation of your part is tied directly to the function. So being a heat-based system, I want to stress that again, that heat-based with orientation of your part, those types of things do go into deciding the optimal orientation. Limitations, on the other hand, yes, every machine in the additive community has a given size, as does every injection molder. They have given shot sizes. So depending on what machine you deal with, how big can your part go is driven by the size of the machine. Consistency, again, I've touched on this. We have found pleasantly surprised with the consistency. We just went through a PM just recently and found that our PM parts before that and the parts after that, not only have we adjusted the machine, but it continues to be very accurate and consistent. Massive and thin details. This technology may not be the best, and really there's not many 3D printing technologies for massive sections, heavy sections. But the nice thing is there are different settings for each type of part, and you can change those settings within the same build. You have a heavy, massive wall part, you have very thin walled, small detailed parts. They can be ran at different settings in the same build, which is a big advantage. For instance, nesting, you can run an 8 to 10% density in your nest, and that is very feasible with the SLS technology. How you nest, there's softwares out there. I happen to do it old school. I nest it myself on the screen for every build, but that's a major advantage, and the software can help with that. So those are some basic design considerations. Again, some of those can be varied by materials as we move on to look at the basic material options that we have. So here's highlighted, I'm sure many of you are familiar with the SLS technology. It's been running the PA-based materials for some time, PA12. It's a wonderful material, well-rounded. And we talked about surface finish, and again, one of those comments about the SLS technology is grainy surface finish. For instance, to give you a reference, PA12 often runs at about a 44 micron particle size. Gives you very nice surface finish. It can have glass bead. PA11, it offers good ductility, a little more elongation as noted there. PA6, this is another nice development by BASF. This actually comes in a few different types. You can get the standard, the mineral-based material, as well as the flame retardant or fire retardant material. The PP1200 is the exciting one. It's polypropylene. It's the same PP-based material that comes out of an injection molder, We've been running it for about 14 months now. Particle size, comparatively, is about 70 micron. So that affects surface finish a bit, but we've had very good luck with it and a lot of success. And finally, the TPU arena offers an elastomeric, a rubbery material. So that this shows the diversity of the SLS technology, covers a lot of different materials. As we move on to post-processing, a very common question as you start to peel back layers of the onion. What does this technology need? You see pictured there our cleaning facility, and what we've done here is actually built the area specific for this. So dust control or powder dust control, that must be taken into consideration. We put in air handling units to keep the air clean. You see a separate room there pictured in the right side of the picture. We actually built a separate post-processing room to keep everything contained. Your HVAC system or your air handling system has to be taken into account. Use filters on your air handling system. Don't let the ducts blow air directly on the machine. Things of that nature. Pre-planning can go a long, long way in success. What types of parts do we build? We build not only various prototype and one-off parts that are varying from size and wall thickness, so we do a lot of prototyping, but we also do serial production. We use this technology for production parts that are repeating. We have one small component that we've printed over 14,000 pieces in the last 12 months. We have another part that we're building several hundred parts. So we use it for both production and prototyping. And again, the production parts are very similar to injection molding. You need gauges, you need quality instruments. It's really no different in how you inspect. Surface treatments are being developed as we speak. In that post-processing arena, blasting is a very common process to clean the surface. Other surface treatments for color, such as painting, we'll get to that in a use case. Plating, all those things can be done with SLS parts. And again, you can build assemblies together as one part, which is wonderful for downstream labor to reduce that. Downstream assemblies, it really helps. As we move over to limitations, again, a consistent environment. This technology wants to be ran in a consistent environment. Whether the season changes wherever you're located, from cold winters to hot summers, the environment needs to be consistent. Simple things like doors and drafts, cold air coming in, things like that have to be taken into account along with humidity. You just want a stable environment. Another limitation or consideration would be the area. How much room do you need? Again, as pictured there, the machine takes a very small footprint, which is wonderful, but the post-processing must be considered. So you have to have ample space, and you need to consider that. And the last thing to consider as a limitation is nearby processes. Though we've got it contained, you will have some powder float. It will get on other surfaces. So you need to understand what processes are you going to put near this. So as we move on to key takeaways, they're pretty straightforward for each for an investment like this. Invest in your facilities. I just mentioned, plan ahead and do your research. I would encourage anybody considering this technology in-house is, after you're done talking to the salesperson, which is fantastic, get out and talk to users, people that have been doing it, and I think you're going to learn some other things. Number two, define your specs. What do you need for your facility? Each facility is going to be different, and you need to consider your own area. And finally, number three, create a weekly ROI. As you invest in this technology, everybody has to have a return on it. You need to understand that. Do you have to run your numbers and have the machine full every day? Can it sit idle 10, 20% of the time? Prepare yourself for, I can really fill it up and have a long run for the weekend. Those types of things need to be considered with this technology of how you're going to operate it, because whether you're in a production environment or a prototype environment, it will vary. So there's a wonderful quote: before anything else, preparation is the key to success. That's with any big decision like this. So those are some key takeaways that need to be considered. So as we move into some actual use cases, this part.
Yeah, Dave, just to rebound on this one, thank you for giving your user inputs on this technology, because you've been operating it. You've been taking the decision to move from outsourcing to insourcing. So that's a good example of things you had to do to go through the technology. And I mean, really, once you know the second point, which is what are the specs you can get from that technology, the minimum features, and really what you will accept as a print job, there are very, very few design limitations. You can put roughly anything into that printer. Of course, you want to make sure that because it's a 3D printer, you minimize the amount of material you're going to use. So that's really more about the CAD part of the part. But once you get the part, you can do anything. And I fully agree. If you know exactly how you want to use it, you will get that result, and you will see your business case working well based on this input, because it will stick to what you had planned. So thank you very much for those inputs.
Very good points, Alban. Okay, so as we look at a few use cases, as we wrap up and look forward to your questions, this component covers multiple aspects of what the material can be used for. You'll see two posts coming off the one side, if you will, in the square window. Those are posts that receive a mating part, and this is polypropylene material, and allows us to heat stake the mating component on. So those square posts get heat staked. You'll see this is a front isometric and a rear isometric view. You'll see the two halves in the middle have a very thin section. That's a live hinge. So these two halves can flex. So there, we're using the capability of a flexible material, but yet it's very durable. So we have a live hinge included here. And that is a preloaded angle. This part was printed in multiple iterations, and we started to understand how that material flexes in that live hinge. So we're using the ability to heat stake, the ability for it to flex. As we move on to the next slide, here's a couple mating components, very small. The picture on the left, overall width is about 24 millimeters. You'll see two pronged or barbed features, we call them Christmas trees. Those flex to receive a snap fit, works wonderfully. In the middle is a C-shaped snap fit or a C-shaped clip. This is a very small part, and all these components go together. On the right side, the part in blue, that's about 8 millimeters wide and about 3 millimeters thick. Again, a very small part that is snap fit into that, and on the back side of this view, we heat stake it into place. So those were CAD pictures. As we move to the next slide, these are actual physical parts that were built. There's the same parts we saw in CAD. The left side, it's now been painted red, minimal benching, so you can actually see the layer lines, which was acceptable to this customer. But those are the actual parts that were built. On the right side, there's that same barbed features on the left and right with the clip in the middle. And this is, again, polypropylene, which runs at about a 70 micron particle size. These are very close-up pictures. The surface finish is acceptable to the customer in this case. And the lower right picture is showing that clip that is inserted, that is heat staked into place, and it holds a mating part. So very fantastic functionality, which is what we were going after in this case. And this product is moving towards production being which would be on the SLS technology. And as we wrap up, one more use case to the next slide. This is a type of tank. It's your basic two-piece tank with a cap. But what's exciting, again, is the ability to print this using additive manufacturing in polypropylene material. The two halves of the tank, the gray and the green color, were actually heat welded together to make a fully functional part, just like in production. And as we move on to the next slide, we'll see those physical parts that were built in 3 separate pieces, heat welded together. And not only did we fill it with fluid for leak tests, permeation through the side walls, which we saw none, we also subjected it to air pressure to check for leaks. We did not do a burst test on this part, but we were very impressed and very excited how it performed holding liquid as well as air. So that's a polypropylene part that is simulating production. So in summary of these two cases on the next slide, the tank assembly is exciting because it was built in the same material as production. Obviously, allowed for a reduction in time and cost. We're estimating tooling about an $18,000 US dollar savings. We saved about 6 weeks. The chemical compatibility of PP speaks for itself, but this was a fully functional part that allowed for functional testing. And to the aerospace application, and we just list a few of the attributes there. This is in the same material and process as production is going to be. We had a live hinge. We had the snap fit barb components. That live hinge was preloaded for a unique fit. We can heat stake mating components. We were able to color it, and again, it produced a fully functional part. This part in injection mold in the US dollars would be approximately $27,000 and would have about a 10-week lead time. So just another use case that I'm sure many of us are familiar with where additive came through. So with that, a few examples, I'll turn it back over to Madeline as we are ready for some questions.
You're on mute, Madeline.
Apologies, I didn't realize I was on mute. Okay, great. Well, thank you so much, gentlemen. That was very interesting. So we can start with some of the questions we have from the audience. Also, feel free to ask questions as they come up during this Q&A section, but do try and ask them in the Q&A section. So the first question is from Luis Martins, who asks, how much in percentage is in global budget investment in post-processing and power? How much percentage in global budget investment in post-processing and power treatment does it represent?
Well, I can speak for a few projects we've seen. In general, if this is going to be your first SLS printer, indeed, there are a few peripheral equipment you need for the breakout station, the nitrogen generator. You need to do probably some work in your facility to host, as Dave was mentioning, the pottery technology. I would say that's probably going to be to double the machine-only budget. But then this is an investment that you have to do only once. If you're growing, if you eventually plan on adding a second printer, you would use the same equipment, so that's only needed once. So if you have a project where you will stick to a single printer, yes, it's probably, I would say, depending on your facility, between 50 and 80K price. Again, you can scale up. There's some more expensive tools. You can have some manual tools, some more automated tools. So there is a way to find and put the cursor where you want to be, but it's an important part of your setup when it's the first time you're going to onboard SLS.
Okay, well, thank you very much for that very detailed answer. So another question that we have from an anonymous attendee is, I'm keen to find out if we can use recyclable material. How is the long-term cost savings? What is the long-term savings like when you switch from conventional injection molding to something like aerospace? Like something like this for aerospace, for example.
Well, I'll touch on that, Alban. I'm sure you've got input also. When comparing head-to-head, because we deal with injection molding also. So it's a wonderful process, especially high quantity. Raw material comparison, roughly, and this is a rough cost per kilogram, if we're going to use it in that unit. SLS powders are generally 10 times per kilogram what a natural polypropylene resin is, let's say, at least here in the US. But that's just part of the answer, is the material cost. It must be considered also, I think, as you digest the cost of an injection mold part, only a very small percentage of that is actually material cost. The rest of it is overhead. It's the injection press things like that. So yes, the powder is, for the SLS technology in the last 3 years, has come down in cost notably. If you're going to compare it to injection mold resin, yes, it's still more expensive, but material cost in the end is only a small portion of the true part cost.
Great. Okay, well, we can move on. Another question, actually we've had similar questions, is can you use SLS in industries like aerospace, and why would it be useful for that sector?
The SLS technology can be used in aerospace. I can say that confidently because we're doing it. But the entire field of additive manufacturing is evolving, as is the ability to write specs, make part prints. Because, for instance, polypropylene now can be injection molded as well as printed. If the print for the component says it needs to be made in polypropylene, often the prints that we see don't specify the process. So, and I know ASTM and other organizations like that are working with, as well as the AS industry, aerospace, as well as medical. Well, now do we need to start putting material and process on a print, or does it matter? So yes, it works for aerospace. If you need glass-filled PA, if you need polypro, if you need TPU, those materials are true 100% materials. Unlike, if this question is coming from other technologies, unlike SLA, well, it's polypropylene-like, it's nylon-like. These materials are legitimate 100% PAs, polypropylenes, depending on which one you have, but they are fully 100% materials. So yes, it can be used for aerospace.
Okay, perfect. And we have a question which I would say is very much for Alban, which is how many parts could you put, for example, in a P100 printer if you were doing mass production?
So the P1000 printer, and the Prodways one is one of the solution. It has a build envelope of 300 millimeters by 300 millimeters by 300 millimeters. I think it's 11 inch by 11 by 11. And there is the P1000X that has a more powerful laser and a slightly bigger Z dimension. So I cannot tell you how many parts you can put, because it depends if you're doing thousands of tiny parts or just a dozen of larger parts. But typically in that volume, if you were to build consistently the same part with a good nesting software, and I saw there was a question about the software also, I don't think that there is any specific software for AM, because it really goes to the designer, where the most important part in software is probably the nesting. And if you start to have to push your optimization, or if you have a lot of different parts, your nesting factor from 5% to 10% is going to really change your ROI also. So the nesting is going to tell you how many parts you can put in that volume. But we've seen jobs with small parts with thousands of parts in the same job. So there is no limitation to a number of parts. It really depends on the size of the parts that you're putting in the machine in that volume.
Great, thank you so much.
To expand on that just a bit, literally, I mentioned earlier we have one part we serial produce thousands of. The most parts we've ever had in a build, it was the same part, relatively small. We put 1,080 parts in one build, and it built very successful, and we've actually done that same build multiple times. Very small part, to Alban's point. There's other things that you can only fit one in, but we've done almost 1,100 parts in one build.
Of course, it really depends on the size of the object, of course, but you can, with efficient nesting, you can get quite a lot of parts into one. Another question, which is there a way to print the first build and subsequent build without a trial and error method?
Well, this one is for you, Dave.
Yeah, very good question. And I have a hunch this came from an experienced person. again, I've been in the industry over 2 decades, and that question is coming from, I'm going to call it the past of the SLS technology. For a while had a reputation of, I'm going to build a part, well, I'm going to have to build it 3 times to get a good one. Those days, at least I can speak from our experience, are hopefully behind us. Yes, you can produce that first part without trial and error. Now, does experience count? It sure does. Knowing thick-walled, thin-walled, how to nest, but we don't do that here. I'll put it that way. We don't price our components that way. We price and we plan for building it once, getting it right, and shipping it out the door. So no, it can be done without a trial and error method.
Great, yeah, that's really good to know. Another quick question on the automotive and aerospace industry. Stefan wants to know, do the printed parts made using SLS pass through automotive or aerospace qualification processes?
Yes, it's possible. I mean, we've been qualifying some process. It goes beyond just the material, because you need to be a qualified supplier. You need to have some ISO certification in some case. But it's absolutely possible to use SLS 3D printing for certified aerospace and automotive parts. And you will find material that match the spec. And then you just need also to have a manufacturing site that will match the requirement from this industry. But there are many known examples of SLS parts that are on board planes or inside cars today as real examples.
That's true. And just going off of that little question, we have something from an anonymous attendee who asks, what are the sectors that have adopted 3D printing the most, ranging from medical device to aerospace, etc.? And also, do we have a statistic of the successful change from conventional to 3D printing, which is a big question.
So talking about sectors, I mean, this goes with the history of 3D printing. If you think about it, in general, 3D printing is the only manufacturing technique that can manufacture holes. So all the rest, you know, the subtractive, injection molding, there is no way to create all that complexity of geometry. And so that's why historically the aerospace industry has been keen on using 3D printing, because it was allowing to make lighter parts. Then the second emerging sector to come to 3D printing was medical, because each individual is different. So if you need orthotics, if you need dental, if you need hearing aids, you need unique parts. And so 3D printing is the only techniques that allow you to manufacture parts that are all different. Think about the hearing aids. It's a sector that is now 100% made through 3D printing, because each individual has a different mold. And this is only possible because of the digital aspect of 3D printing. So clearly aerospace and medical have been strong sector in general for 3D printing. And then in the recent years, the evolution of the technology, the robustness, the cost, the reliability has opened doors to the traditional manufacturing sectors. So now we will find 3D printed parts in sectors that would not be considered before. Automotive, that used to be, you know, very price sensitive, is now widely using 3D printing. Even consumer goods in the industry, there is no limitation anymore to the vertical segments that can use 3D printing, and SLS in particular for functional parts. But it's true that aerospace and medical have been a long-time user of this kind of technology.
Thank you very much. So one person has a few questions, so I am just going to group them together. First, what reuse to virgin powder ratio do you run on BASF's P11? Do you find it slower to print SLS P11 over PA12? And isn't the number of parts you can pack in a build dependent on the laser run's scan time? What is the max scan time you would run?
Okay, I'll take a few of those questions around material indeed, and thanks, Christopher, for the questions. So first, refresh rates and recyclability. So we see today material in SLS that range from a 50-50 refresh rate down to 10%, and even you could go to 0% of some of the material. So you can find some material that can be fully reused. Just to be clear, what we call recyclability is what do you do with the powder that was not sintered. So it has been exposed to heat, and the grain will slowly age as they go through these heat cycles. And so you want to bring fresh powder to the mix every time you build, and that's your refresh ratio. We're working hard to continue to improve those refresh ratio. That goes working with the chemists so that we can do that. So again, we have a few materials that can get to very high refresh rate. Ideally, being at a 25% is good enough because you're already using 10% of the volume as sinter parts. So as soon as you get close to 25%, that gives you a fairly good economic usage of the powder. Now, with respect to the different powder, I saw there was some question also on which powder to use for orthotics application. So PA11, let's do a quick review of PA12, PA11, PP. PA12 has been widely known in the past. It's a generic prototyping material. PA11 will indeed be a good use for medical application. It has slightly more ductility and more elongation. That is a better fit. It has a medical grade, so anything that has a skin contact or a medical application will appreciate using the PA11. And so we have, for example, at Prodways, a medical grade PA11. And PP will give you the value of PP that it's a known material. And they've made a very important comment. It's true polypropylene. It's not a polypropylene-like. So, and that's why it's a cheaper material, and it gives you access to finished parts for functional parts with polypropylene. With respect to the last part of the question, the number of parts you can pack depends on the laser scan time. So the number of parts you can pack is just a geometrical feature. So you take your 3D volume and you just try to put as many parts as you can in this volume. Then the build time and the duration of the build will depend on the number of parts, on the geometry, because that will change the scanning time. It will not change the rest of the process, but the scanning time will depend on the number of parts.
Okay, thank you very much. Well, we're coming to the end, but we can try and fit a few more questions in. Another good question another question that I saw was, when printing thousands of parts, what is the accuracy and repeatability that can be achieved in batch production?
Yes, I can speak to that in the way of, as I flip through my notes for that. We're holding the tolerances that I pointed out earlier, in that we're staying within 0.25 of a millimeter, well within that. And not to convert units on you, but our print for that component, it's about 40 millimeters long by 20 millimeters wide, and we're holding easily plus or minus 1/4 of a millimeter. They're very consistent. We do find some deviation, whether it's in the middle of the build platform or it's on the outer edges, and by variation, things besides tolerance dimensions is color. So color is also an aspect, excuse me. Color is something to be taken into account. The polypropylene material is a white material, but it can vary in color as we recycle. Alban touched on recycling, virgin versus, we've gone, for that person that asked the question, we've ran 100% recycled material just to see what it would do. And the color starts to vary a bit, but tolerances stay very robust in serial production.
Okay, great. And maybe for the last couple of questions, can the most durable material for, I think, in using polymers, replace metal parts?
Yes, it's a mixture of material selection and also doing the right design, the right thickness, the right simulation to make sure that your part will be able to match the mechanical force you expect from that part. But there are many good examples of design that were able to replace a metal part with a plastic part. You have got some high strength plastics on the glass field one. It really also depends on the type of I would say force you will exert on that part. it's a shock that you need to absorb, if it's a constant pressure that you need to exert on the part. So that will change the material you will pick. But definitely, there is some high performance polymer that are fairly easy to run, and that will give you an alternative to metal parts for sure.
Okay, well, thank you very much. That is time. There's only a few that we have not answered, but do feel free to contact Prodways or PERIDOT to ask further questions if you're still curious about anything. Thank you so much, Dave and Alban, for being here today, and thank you to all the attendees. I hope you enjoyed the webinar, and don't forget you can find it on the 3D Natives YouTube channel. It will be up in the next couple of days.
Thank you everyone for attending, and thank you Dave for your testimony. It was really great. Thank you very much. Thank you, Madam.
Yes, thank you all. Appreciate it.